Hello and welcome to Maths on the Move, the podcast from plus.maths.org. I'm Rachel Thomas.
And I'm Marianne Freiberger. Rachel, how far away do you think we are from discovering extraterrestrial life?
Oh, I don't know. In terms of distance, I'm hoping quite far. In terms of time, I don't know, centuries probably?
Well, I have it on pretty good authority that probably we're only 2 decades away from discovering alien life.
Well, that is much sooner than I expected.
And here's another question. How far away do you think we are from creating life in the lab?
Oh, that has to be centuries away. I don't think we're anywhere close to creating life in the lab.
Well, I also have it on good authority that we're only 5 years away from creating life in the lab, though apparently people have been thinking that for 20 years.
Well, then we must be at least 15 years out if they've thought it was 5 years away for 20 years. And I must say, I don't really want Frankenstein's monster suddenly appearing on the streets. But anyway, who is this good authority you have these estimates from?
Well, I talked to our good friend, Mario Livio.
Oh, Mario Livio, he's written us some lovely articles. Didn't he write us one about symmetry and one about the Hubble Space Telescope?
Yeah, exactly, among others. And he's also an internationally renowned astrophysicist and author of many popular science books.
That's right. But hasn't he just published a new book?
Yes, he has. It's called Is Earth Exceptional? The Quest for Cosmic Life. And he's written it together with the Nobel laureate Jack Szostak. In the book, they look at research that's been done on 2 questions related to what I just asked you. The first question is there life elsewhere out there in the universe? And the second is, how did life emerge here on Earth? I had a chat with Mario, and I started off by asking him what the book is all about.
So the book is about 2 main things. One is the origin of life on Earth, on which Jack is one of the world experts because he does much of the current research on that topic, and on the search for life in the universe by astronomers, both in the solar system and around other stars. So it's these 2 topics put together.
And what gave you the idea of putting them together? Because often they're treated like separate things.
Right. So I think that this is actually one of the main, perhaps, contributions of this book. The fact that we point out that these 2 efforts are really have a very strong symbiotic relationship. Because here is the thing. If, for example, let's say that astronomers were to discover life elsewhere in other places, that would probably mean that nature was able to do that given the right conditions. And that means that, trying to do that in the laboratory is also possible. And this is what Jack and his collaborators and a few others and so on are trying to do. Similarly, in the other direction, if they actually will show that there is a reasonable pathway from chemistry to life, then it means that, okay, if they can do it in the lab, then perhaps nature can do it too in other places, and that provides strong encouragement for the search for life in the universe. Plus, it also tells us what are the conditions that are needed, for life to emerge. So that helps the astronomy. So really, these 2 efforts encourage each other and support each other in a very strong way. And this is why we decided to combine the 2.
And can you summarize, if it's possible at all, what do we know about the conditions that are necessary?
So, of course, we normally talk about a planet being kind of Earth-like, and by that we mean a rocky planet. not a planet that is all gas or, and so on. And we normally talk about this concept, which is called the habitable zone. The habitable zone is that Goldilocks zone, which has it's a range of distances from the central star, where the temperature on the surface of the planet is neither too hot nor too cold, so that it allows for liquid water to exist on the surface of the planet. Because we think that some liquid solvent for sure, and water is perhaps the best, or maybe even the only one that can do the job, is needed for life to emerge. So we look at planets that are in that habitable zone. Now, this is just put it in very, very rough terms. I mean, there are many other things that are important that have to do with the composition of the atmosphere, with the mass of the atmosphere, the type of the central star, the rotation of the planet, and all kinds of things like that. But these are at least the very basic things that are needed. And these are the ones that guide most of the astronomical search for life elsewhere. Namely, we look at planets in the habitable zone of their host star, and then we try, if at all possible, to characterize the conditions in the atmosphere of those planets.
And when it comes to the origin of life here on Earth, what are sort of the main pillars of knowledge that we have that would describe how that happened?
Yes, so that's actually quite amazing how much progress has been achieved in the past 20 years or so in the laboratory. The thing is the following. I mean, we used to think that there was some sort of a primordial soup of chemicals, and out of that primordial soup, somehow, the building blocks of biology emerged. And that's in some sense true. But for example, there was a famous Miller-Urey experiment which showed that, okay, you take a certain combination of conditions you think characterize the Earth's atmosphere at early times, and you pass some electric sparks through that, to simulate lightning and so on. And certain things closely related to amino acids, which are the building blocks or proteins, were formed. And that was thought to be a great success. Now, it was a great success in the sense that it inspired lots of such experiments. But today, we know that that's not what's needed. We don't want thousands of chemicals to be created and then hope that somehow from that something will happen. Rather, what we need is a situation where a few key chemicals are created in high concentrations, and that those can then, lead to things. Now, as I said, the success so far has been astounding, even though not complete. For example, RNA has, RNA is made of phosphates and sugars and some bases. And those bases, they contain 4 building blocks, which are called nucleotides, which are denoted by certain letters, U, A, T, yes, and so on. And so far, the people who deal with the origin of life have managed to show clear paths where the chemistry that we think was on the early Earth could lead to the formation of two of those nucleobases. So really that, happens in the lab. I mean, you just start with the right conditions and it happens in the lab. Now, as I said, it's not complete because there are two more which we haven't managed to do yet, but two were done. And plus, that same chemistry, precisely that same chemistry that produced these two nucleobases, also, it turns out, produces as many as 12 of the 20 amino acids that form all life on Earth. 12 of them. So we know that too, that could have happened on the early Earth. So there are many remaining questions, but it shows that at least it looks like they are progressing in the right direction.
And so if it's been possible in the lab to create these bases for RNA and other, I think, did you say amino acids? So how far away are we potentially of creating life in the lab?
So I'll be honest with you. I've been talking to Jack Szostak, my co-author, about this problem because he's one of those who do these experiments. I've been talking to him for, maybe 20 years, maybe more. And every time I ask him, okay, so when are you getting there? He tells me, I think in about 5 years. But this has happened already like 4 times during the 20 years. So while they have made enormous progress, incredible progress, there are still unsolved questions. Like I say, 2 of the nucleobases have not yet been formed. There are problems related to how do you attach the phosphates to those nucleotides precisely. There are many questions related to that. And then there are questions related to the cell, to the biological cell. All of these things happen in all life as we know it inside cells. So for cells, they know how to make some vesicles that can even grow and, multiply. They can do that, but they don't have yet the right composition of the membranes of the cells that surround them. They don't know how that exactly was formed, and they don't know how those cells evolved eventually. What we do know is that the first cells of life on Earth were probably much simpler than the cells we see today.
And what did you learn then by combining these insights from biology and chemistry with the astrophysical approach?
So you see, in the same way that Jack and people like him think that they are really close to solving the problem of how could an early cell have emerged on Earth, astronomers also have made incredible progress in the last 30 years. You may remember that before 1992, we did not know of a single planet that revolves around the star other than the sun. In 92, they discovered planets that revolve around the pulsar. Those cannot have life on them. The first time that planets around stars that are a bit like the sun were discovered is 1995. So, just 30 years ago, until 30 years ago, we didn't know of a single other planetary system other than our own. And now we know of more than 5,000 of those. And in fact, when you do the statistics for the whole Milky Way, they could be in the hundreds of millions or maybe even a billion such planets. So that is a huge progress. Now, the question is, how many of those are in the habitable zone and so on? So we now discovered many that are in the habitable zone. For example, there is a famous system, it's called TRAPPIST-1, which is a star that has at least 7 planets around it, and 3 of those are in its habitable zone. So, we were very hopeful that once one looks in the atmospheres of these planets, maybe you can find some biosignatures, some signs of life. Things like, a high abundance of oxygen, or things like an out of equilibrium type of thermodynamic situation, like there is in Earth's atmosphere, because Earth's atmosphere, because of life, is not out of thermochemical equilibrium. So we were hoping to find that. But in the same way that it turned out to be not so easy on the origin of life side, it turned out to be not so easy on the astronomical side. For example, right now, it appears that perhaps those habitable zone planets for TRAPPIST-1 perhaps don't have an atmosphere at all. So suddenly, planets that appeared to be very promising turned out to be perhaps less promising. So I think that, again, if you ask me, when will we discover life? I will say probably within 1 to 2 decades, we'll discover life. Or at the very least, if we don't discover life within, let's say, 2 decades, we may be able to place some meaningful statistical constraints on how rare life is, even when the conditions are perfect for the emergence of life.
Yes. I mean, one of my questions was going to be, in your estimation, from what you know now, how much of a freak accident is life?
I have no idea, and I cannot make a guess, and I can explain why. You see, from the origin of life experiments, we discovered plausible pathways from chemistry to at least some parts of the components needed for life. However, we have also discovered that this pathway requires a certain sequence of events that must all happen in the right order at the same place. And we cannot actually at this point even estimate the probability of that sequence to happen. So at this point, I would say that we have no idea of what is the probability for life to emerge, even when the conditions are there. And as a result of this, I cannot give an answer. People tell me, well, but if there are 1 billion such planets in the galaxy, then surely, somewhere life is it. I said, no, not surely. Because I don't know what the probability is for life to emerge. So I cannot tell you whether 1 billion is a large number or a small number.
So what did you, in writing your book and putting these two aspects together, what did you learn? What were some key insights of putting those two approaches, like the origin of life on Earth and the search for extraterrestrial life? What did you learn? What were new things that you learned?
One of the things is what I just told you, namely that it's great to discover lots of habitable zone planets, but at the same time, once I learn what is required in the origin of life, I cannot say with any certainty that there is life out there. So for example, to answer the question if there is life out there, will have to come from the astronomical side, because the biological, the biochemical side does not give me the probability. So I have to search and find out what happens. So if by the end of 2 decades we searched 100 of the best planets where life could have emerged and we didn't find anything, no biosignature. And by the way, I'm talking about discovery of very simple life. Yes, I'm not talking about finding crocodiles up there, you know, and so on. Simple life. If we don't find it, then at least we will be able to say that probably the probability for life to emerge, even when the conditions are right, is smaller than such and such. So, and again, you know, since we will not have billions of such planets that we have observed and characterized, this will only be an estimate. Because if you only studied 100 such planets, then okay, maybe you can say that the probability is less than 1%, but you cannot say that it is less than 10 to the minus 10, you know, and so on. So, but it is really something that comes only from the combination of these two things. Now, there are other things we have discovered. For example, there are some things that astronomers are also looking in the solar system. Of course, Mars is a prime candidate, and you know, just a few days ago, I mean, they announced that there was this mission called InSight, which did the seismological measurements on Mars, and discovered that most probably there is lots of liquid water of the order 6 to 10 miles deep. So not on the surface, but somewhere deep. So it will be interesting, very interesting, to discover whether at any point we find any signs of past life on Mars. Because, you know, Mars was formed at the end of the day from the same part of the protoplanetary disk where the Earth was formed. So yes, okay, because it is smaller and so on, it cooled faster, it's lost its atmosphere, but there is no real reason why it couldn't have had some early life, you know, 4 billion years ago. And if we don't discover any of that, that would be telling us something.
Now, thinking about a previous book that you've written, and also taking a mathematical angle, since we're like a maths magazine. So you've written a book about it's called Is God a Mathematician? About sort of the unreasonable effectiveness of mathematics, that people often call it, that mathematics is so incredibly useful in describing the universe, and some people would even claim that the universe is inherently mathematical. Does that somehow shed light on it, or does that come in to these ideas that you're exploring into the book somehow?
Well, you know, of course it does. I mean, look, almost everything I mention has a mathematical aspect to it. When I tell you that we are looking at habitable planets, the whole concept of having a habitable planet, of course, comes from a theoretical model which says, what will happen to a planet that is such a distance, and can we calculate the conditions in its atmosphere and things like that and so on. All of those are mathematical studies, you know, or studies at least that involve mathematics. So of course it is like that. On the biology side, you know, biology by its very nature is a more experimental discipline than let's say fundamental physics. When I talked about Is God a Mathematician, I was referring mostly to fundamental physics. Yes, biology deals with very complex systems, So, I mean, nobody tries to explain why Newton wrote his laws by finding the physical processes in his brain. You know, I mean, but of course, at the end of the day, everything is governed by the same laws of physics. And when we say that, you know, we look at the chemistry at planets around distant objects and so on, we make the immediate assumption that the same laws of physics and chemistry apply there as they apply here. And it is astronomy that actually tells us that that's the case, because we look at the galaxy that is 10 billion light years away, and we see that, you know, as far as we can tell, precisely the same laws of physics apply to the light from that galaxy and so on. So it is at the background, but of course it doesn't enter into the actual calculation of the biological processes.
Wow. So mathematics really does underlie everything, which is what we always thought. And Mario's book sounds really fascinating. When is it out?
Well, as it happens, it's out today. It's published by Basic Books, and it's called Is Earth Exceptional? The Quest for Cosmic Life. And it's written by Mario Livio, who we heard from in this episode, and by Jack Szostak.
Great. I'm really looking forward to reading it. To get a taster of Mario Livio's writing and to see reviews of some of his previous books, including Is God a Mathematician?, go to plus.maths.org and search for Mario Livio. We'll also put links in the show notes. Thanks for listening, and bye-bye for now.